Okay, in this video I'm going to continue on with exercise 6A of the book Fundamental Applied Mathematics. We're on page number 157 and the question is 11. It's from the Leaving Certificate, Ordinary Level 1983. It reads: a particle of mass 20 kilograms is pulled along a rough horizontal plane by a string which is inclined at 30 degrees to the horizontal. If the tension in the string is 80 newtons and the coefficient of friction between the particle and the plane is 1/3, calculate the horizontal and vertical components of the tension, the normal reaction between the particle and the plane, the acceleration of the particle, and the total work done in moving the particle through a distance of 0.5 meters. So once again I've just drawn the free body diagram, noting the unit vectors, I hat and j hat. We have the normal force in the j hat direction and we'll say the weight vector in the negative j hat direction, frictional force in the negative I, and we have the tensional force. However, it's both in the I and the j, so we must resolve it into its component unit vectors. Noting, of course, that the coefficient of friction is 1/3. So let's just resolve this quickly. So we have parallel to the I hat first, parallel to the j hat. So these are the two vectors, which when added together will create the vector 80 newtons. They're at right angles. This is t sub y j hat, and this is t, I'll get rid of this line, don't need it anymore. This is t sub x I hat. Both of them, of course, are positive because they are in the first quadrant. So this is going to be 80 times the cosine of 30 in the I hat direction, and this is going to be 80 sine of 30, the j. Alright, so I'm just going to rub those back out there so I give myself some more room. So let's find that out. So the sine of 30 is equal to half, multiply that by 80, of course, and we're going to get that t sub y is equal to 40 j hat units. And then 80 times the cosine of 30 gives us 40√3, gives us 40√3 units in the positive I hat direction. So let's, well, of course, that's the tensional vector, okay? So that's the first part sorted. Next we're asked to find the normal reaction between the particle and the plane. Now it is not the case to say that it's just negative 20g. Why? Well, the answer is, look, we have additional forces. We have in this case 40 units in the j hat direction also. So let's apply, just to confirm that, let's say the tensional force wasn't there. Then we'd apply Newton's second law. We'd say the sum of the forces is equal to the mass times the acceleration. Then we'd have n minus 20g is equal to, and the particle isn't accelerating in any particular direction, so you'd say it's 0, and therefore you get n is equal to 20g. Alright, however, that is not the case that we have here. We have n minus 20g plus 40 is equal to its mass, which is 20, and the question is it accelerating in the j hat direction? And the answer is it isn't, because we're told it's being pulled along a rough horizontal plane. So that implies basically that it isn't leaving the plane. So we say the acceleration in the j hat direction is equal to 0. So again, we eventually get that n is equal to 20g minus 40, and that's going to be equal to 20 multiplied by 9.81 minus 40, giving an answer of 156.2 newtons. Oh, 156. Alright, so I don't think we need that piece of information anymore. What we do in actual fact, we do, because we have to calculate the frictional force. And we know that the magnitude of the frictional force is equal to the magnitude of the normal times the magnitude of the coefficient of friction. So in this case it's 156/3. And that's going to be equal to 52. Alright, so we have 152, we'll say here, and that's going to be the frictional force. Its magnitude is Newton, or sorry, its unit is newtons, so we'll say that the frictional force is equal to negative 52 I hat. Alright, because clearly it's going in the negative I hat unit vector direction if the particle is being pulled in the positive I hat unit vector direction. Next we're asked to find the acceleration of the particle. So we know it's moving in a positive I hat direction, so let's apply Newton's second law again. So we'll find that 40√3 minus 52 is equal to the mass, which is 20, times its acceleration. So let's just work this out. We have 40 times root 3, take away from that 52, and divide that whole thing by 20, and we get an answer of A is equal to 0.86 meters per second squared. Alright, finally we're asked to calculate the total work done in moving the particle through a distance of 0.5 meters. Alright, so remember of course that work done is equal to, what is work done equal to? Geez, I'm after pulling a blank now, to be honest. Work done, force by distance, isn't it? Force by distance. Alright, or force by displacement in actual fact. So this time, let's just read this again. It says the total work done in moving the particle through a distance of 0.5 meters. So my reading of that is that it takes the resultant force. It's not the force just of the tensional force, excuse me, it's the resultant force. So it's going to be the following. It's going to be the sum of the forces times the displacement. So that's going to be equal to, well, 40 minus 52 times the displacement, which is 0.5. That's going to be equal to the work done. Okay, like so. Work done, of course, is measured in joules. So 40. Why is it 40 minus 52? No, that's incorrect. It's 40 root 3. Let's rewrite that. Excuse me now. That's 40 root 3. 40 root 3 minus 52. So 40 times root 3. Take away from that 52. And then multiply that by 0.5. Oh. Get an answer of 8.64 joules. Alright, so the last exercise we've got to do is just check the answers. So I'm just going to go to the back of the book, and we're on 6A question 11. So what was the first one we need to guess? The coefficient of friction. So we had 40 newtons. Yeah, just bear with me now because the answers are different here. It says it's 69, so I'm just going to calculate the I component of the tensional vector. 69, yeah, that's correct. Okay, so the tensional vector was calculated correctly, the normal vector was calculated correctly, so was the acceleration, and finally the 34 joules. That's incorrect. 34 joules. Okay, I have a feeling here that the book is after just calculating the work done by the tension. Just the work done by the tension. So let's just go ahead and do that. Okay, so that's just just the way the question is phrased. So I obviously read that incorrectly. So once again, work done is equal to force times displacement. So the work done is equal to 40 root 3 times the displacement, which is 0.5. The work done therefore equals, so it's 40 times root 3 multiplied by 0.5, giving an answer of 34.6. So in actual fact it should say the work done by the tensional forces. Alright, so thanks for watching. Please pass it on to your friends and subscribe to my channel.